Hello, AP Calculus AB students, and welcome back to yet another lesson on Topic 1, Limits and Continuity. Our focus for today is on our first of 5 theorems, not today, but for the entire year. We're going to cover one theorem today and actually 2 total theorems in this unit. So by the end of Topic 1, and we have about 8 units throughout the year, you're already going to know 2/5 of all of your theorems. Today's theorem has the fun name, the squeeze theorem. So let's jump right into it. Imagine that someone tells you there's this unknown function f of x. You don't have an equation to describe it. You don't have a table. You actually only know important information about the function based off of 2 other functions. You know for whatever reason this function f of x, which I'll demonstrate in red, is greater than the function 3x, right? It says 3x is less than whatever f of x is. And at the same time, f of x is also less than x cubed plus 2. All right, so first, let's see what we actually know about our function f of x. And in order to do that, we're going to take a peek at the graphs of 3x and x cubed plus 2. So let's go ahead and try plotting those 2 functions. Now, 3x I think isn't too hard, right? Slope of up 3 over 1. X cubed plus 2 might throw you for a bit of a loop. However, you should know it's the parent function x cubed shifted up 2. But since we have a graph here, and we're only looking on the interval from -2 to 2 inclusive, right? These brackets over here mean we include -2 and 2. You might just want to try substituting in all the numbers between -2 and +2 into both the functions. It's a pretty quick and easy way to make an accurate graph. I'll do y equals 3x without that though. We know it has a +0 at the end, so it starts at 0, 0, goes up 3 over 1, up 3 over 1. And I don't actually have to go any further. I'm just looking between -2 and 2. You can if you'd like, but I think I'll leave mine here. Down 3 over 1, down 3 over 1. So here is the piece of the function, the line segment, if you will, for 3x. And then for x cubed plus 2, let's see what happens if we just substitute each of these in there, right? If I substitute in -2, and I'll just do this off on the side, -2 cubed plus 2, this is going to be -8 plus 2. -8 plus 2 is, of course, -6. They actually intersect right there. So maybe this would be more accurate if we had some equal to signs, if they're going to be equal to each other at the end. Then we have, let's see, let's do -1 next. That's going to be -1 plus 2, which is +1. That brings us up right here. And then I know this is just shifted up 2, so when I substitute in 0, I'll get 2. And then through symmetry, I think we're just going to repeat each other out here. So I bet if I substitute in 1, right, the symmetric point is going to flip up here. And then if this one is down, looks like 6 down, 8 down, I bet this is going to go all the way up here. But let's try just in case. Let's substitute in 2. That's 8 plus 2 is 10. Yeah, that makes sense. And so we end up with 2 comma 10. And so we end up with a graph that looks something like that. Yeah, there should definitely be some equal to signs there, but we'll fix that in the future. All right, now we have these 2 graphs, right? And we're going to go ahead and sketch a possible graph of f of x on the same coordinate plane. Now, f of x doesn't have to be continuous here, right? You could pick up your pencil in various spots. However, if you want to try to draw it to be continuous, not a bad way to go. So let's go ahead and do f of x in red. So we know that f of x has to be greater than 3x and less than x cubed plus 2. But what does it mean if functions are greater or less than? Well, these equations over here actually represent the outputs. The inputs are just the x values, right? -3, -2, -1, they go side to side. The outputs, so for example, if I substitute in x equals 1 to all 3 of these, the answers are what need to be in this order. So the less than greater than is talking about up and down. So for example, if I looked at the x value, let's do -1. Here is -1. Now, -1 can have outputs anywhere on this vertical line, right? -1 comma 5, -1 comma 10, -1 comma 0. This yellow function is -1 comma 1. So we have all sorts of different outputs on here. The question becomes, though, where does f of x's output have to be? And based on this inequality, f of x has to be greater than 3x, so it has to be above this one, and less than x cubed plus 2. That means it can be anywhere in this space, and it doesn't matter what. You can put it right in the middle if you want, and so on and so forth. There's a whole bunch of points here. It doesn't matter where you put them. However, and these equal to's are pretty important because these two have the same point at -2 comma -6. I think f of x has to be right here so that it's technically not less than or greater than, it's equal to all those three, which is fine. And then your function can do whatever you'd like it to do over here. Up, there's another equal to spot, and then it kind of sits somewhere over here, right? So it could look something like this. Easy enough, right? We don't know what it looks like, but it definitely needs to be in between those two. All right, so let's look at C. What can you determine about the value of f of 1? Well, f of 1 is this point right here, yeah? So you might be tempted to say, oh, well, f of 1 has to be equal to, what's the y value? 3. But we actually don't know that. And I'll put a little question mark over here. And the reason we don't know that is because f of x does not have to be continuous, right? We said that up above. So my function could actually, and this is going to be a little tough, I'll probably have to just kind of mess with it here, but that's okay. Our function could actually have an open circle right there. And so we could go through, do whatever we're doing, skip through that part, and then finish off the end, right? It doesn't have to be continuous. And so that's a little bit interesting in that we're not actually sure that f of 1 is 3. Now, if they said it was continuous, then certainly we'd have to pass through there in order to satisfy this. So that's a little bit of an interesting piece. But what about the limit? Well, I'm pretty confident that because these two functions start to kind of squeeze together as we get closer and closer on both sides, that I'm pretty confident that the limit certainly has to equal 3. There's no other choice, right? Either there's a point there or there isn't. But regardless if there is a point there or not, we are getting closer to that spot. And so the limit does have to be true. So we'll make a note up here that f does not have to be continuous. So we kind of have two options at f of 1 equals 3. Either it does equals 3 or it doesn't exist. Those are your two options, but those are pretty different, right? Either you get $3 or the answer doesn't exist. However, I am very confident that the limit equals 3. So now that we have kind of this graphical interpretation of this weird triple inequality up here, let's go ahead and discuss the first of our 5 total theorems that you're expected to know and reference throughout this year. Now, a theorem is a statement which is always true as long as certain criteria are met. They will say, if these 3 things happen, then this 4th thing will always happen. Okay? I'm going to ask you to break down, every time we do a theorem, into 2 pieces by asking the following 2 questions. First, what are the criteria that must be met to use this theorem? And 2, now that the criteria have been met, what does the theorem guarantee? Our first theorem, as mentioned above, is the squeeze theorem. So let's see if we can analyze the theorem and answer questions 1 and 2 about it. So this, sometimes it's called a sandwich, by the way. The sandwich or squeeze theorem says, if f of x is less than or equal to g of x, which is less than or equal to h of x for all values of x, when x is near, maybe that should be in quotes because it's not a very mathematical word, right? For when x is near a, except possibly at a, and the limit of f of x, and I should probably color code this again too, so let's do f of x. The limit of f of x, the smallest function, equals the limit of h of x, the largest function, and they both equal a value, then the limit of the middle function equals the same value. Now there was a lot going on in that sentence. However, hopefully you're starting to see the similarities of the squeeze theorem and what we did up above. But let's go ahead and try to break down this weird terminology, and then we'll relate that back to the opener at the top. So first, what criteria must be met in order to use the squeeze theorem? Well, the criteria are almost always after the if. So we are looking for the if. And in this case, we have if this. So we need to know f of x is less than or equal to g of x, which is less than or equal to h of x. Is that it for all values of x when x is near a except possibly at a? That kind of all gets rolled into this. It's somewhat implied. And this is still part of the if, right? If this and that. So both of these need to happen when there's an and. So not only does this have to happen, and the limit as x approaches a of f of x equals this limit for h of x equals L. So the limit as x approaches a of f of x must equal the limit as x approaches a of h of x, which equals L. So if you have this ordering of functions and you find a specific x value where the smallest function and largest function have the same limit, then, well, what can we guarantee will happen? Well, then the limit of the middle function, g of x, must also equal that same value. And I did note that the less than or equal to that's up here doesn't necessarily have to happen, right? In mine, I probably should have put it. Oops, awkward. But it doesn't have to happen. And for mine, again, I think I probably needed it because they shared the same point down here. But it is okay if you don't have it. It'll still work out. Now, do you see what happened here and how we could have seen this graphically up above? What they're saying is that if you find an x value where the two limits are the same, and in fact, I think that happens twice on here. We're just going to look at the gold and the green. We're going to completely ignore the red. Are there any values on here where the limits are the same? Well, certainly. There is one value right here. When x equals 1, the limit as x approaches 1 of all three functions, right? So the limits of both, and what did I call them? Well, we have green and yellow. So the limits are, we're going to say equal, poor notation. And then over here, the limits are also equal. As we approach, we'll say -2, the limits are equal. So what the squeeze theorem says is if you have a top function, in this case yellow, and a bottom function green, and there are spots where the yellow and green have the same limit, then red must also have that same limit. Versus somewhere in the middle, yellow and green at -1 certainly don't have the same limit, right? This is 1 and this is -3. And so red is not guaranteed to have that limit. That's all the squeeze theorem says. Right? Now, it's a nice introduction because this one is pretty darn, approachable. It makes sense that if you have this ordering of functions and these two have the same limit, then the one in the middle better have the same limit as well. Okay, so what I really have for the rest of today is just a few practice problems. We're going to talk about what's expected on the AP exam, in particular the free response section, and also the multiple choice briefly. We'll talk a little bit about the structure because this class is actually a pretty quick one. So let's go ahead and jump into our practice questions. So we're going to try answering the opening question to the day. Even though there are several questions, we'll condense it down into one important one. And we're going to use the squeeze theorem as our justification. Now, justifying an answer using a theorem is extremely common on the FRQ, the free response questions section of the AP exam. And my somewhat conservative estimate says you're going to have to do this at least twice on the free response section. Speaking of, and we should definitely reference this over and over and over again so you don't get surprised when you hit that AP exam, the AP exam is composed of two parts. There's a multiple choice section, and there will be 45 questions there. Some of those questions are calculator active, some are not. We'll dive more into that later on. And then we have the free response question section, which has 6 overarching questions. However, each question has multiple parts. And I would say on average, we have parts A through D on each of the 6 questions, which means on average there are approximately 24 short answer questions. So 6 overall questions. So each of these 6 questions will give you a stem, an introduction to the problem, and then they'll ask you probably 4 questions about that stem. So it's really kind of 24 short answer questions. Out of those 24, approximately 2 of them are going to ask you about theorems. Justifying a theorem is extremely important. Now, if it isn't a theorem and you're actually doing some math here, you are always expected to show a setup, what are you trying to solve, and an answer, what did you solve. Justifying a theorem is very similar. They're going to ask you for what had to be true, which is like the criteria that we discussed on the previous page, and then what does that show? That's the then. What is the theorem stating? Now, you don't actually have to state the theorem on any AP question. However, I think it's a nice thing to do. It's good to go through and reference. So let's go ahead and try this. Let f of x be bounded on this interval. Find and justify the value of the limit or explain why the value cannot be determined. Okay. Now, what you might be tempted to do, and you're going to want to hold off on this, I'm going to do several things wrong as we go through. You might say, oh, the limit as x approaches 1, so you'll say, oh, 3 times 1, that's 3. Got it from there. And then you'll say x cubed plus 2, that's also 3. And then you might say, okay, cool. Therefore, the limit as x approaches 1 of f of x equals 3, because you're like, this was 3, that's 3. You would probably earn 0 points on this question. I do have to tell you, this is the right value. We saw that previously. But this would be considered a bald answer. There's no actual correct work leading up to it. And so unfortunately, on a free response question, if you don't show what you're solving and you just put an answer, you usually receive 0 points on that question. The setup is arguably more important than the answer, because the setup is what we call entering into the problem. And if you don't enter into a problem, you're usually not eligible for the rest of the points in that problem. So how do we enter into this problem? Well, first, you should probably look at this and say, okay, they're asking about a justification of a limit. And there will only be one theorem that justifies a limit. Right? If you're going to justify a limit, then that will be the squeeze theorem. There is no other theorem that justifies a limit throughout the entirety of this year or next year. Okay? And if you're going to be doing a theorem, you need to figure out what needs to happen in order to use that theorem. And here's where a bit of memorization comes in handy. Okay? We need to know the if part of this theorem. What has to happen to use the squeeze theorem? You can look back to the previous page if you want, but I'm going to start with this guy right here. Now, the one thing we don't want to do is I don't want to say if, right? You might say if 3x is less than, I'll put the equals on here, it doesn't really matter in this case. Now we'll keep it off, we'll match it, is less than x cubed plus 2, right? If this is true, and you might say, well, why wouldn't you want to say if? The theorem says if. If makes it sound like you're not sure if that's true or not. You might say, if this is true, then I can conclude this. Well, cool. Is that true? You're making this hypothetical. If this is true, that is true. You're telling them you don't know how to read if you say if, because they told you right here. So we could say something like as, or because, something like that. So, as this is true, and there was a second part to the squeeze theorem, wasn't there? Right? And now we're going to need a limit. The limit as x approaches 1 of 3x equals the limit as x approaches 1 of x cubed plus 2. And it's not enough to stop here. How do I know that those are actually equal? What do those equal? Well, 3 times 1 is 3. This is 3. I'm just going to say 3. We don't need to show the work to get there. We showed the setup and the answer. So, as this was true, and these limits were equal at 1, then, and I'm going to go ahead and put this in parentheses, It's totally okay to leave off the parentheses. I mentioned, though, that you don't actually need to cite the name of the theorem. I think it's good practice. There's only 5 theorems, and if I say, what's the squeeze theorem, you should be able to tell me. It makes it easier to review. Then, by the squeeze theorem, the limit as x approaches 1 of f of x equals 3. That's it, right? It's a pretty simple setup. The only problem is there's that bit of memorization. What had to happen and what happened. We don't want to do if, because if makes it sound like you're not sure. You can cite the theorem or not. And that's it. Ta-da! So, it is actually fairly unusual to see the squeeze theorem as an FRQ. Honestly, a couple of years ago, I used to really just gloss over the squeeze theorem. I taught it for like 10 minutes. I'm like, that's a silly theorem. No one would ever ask you. And then kind of back in like 2017, 2018, give or take, they had one part of a free response question that was all about the squeeze theorem. And I was sad. I don't think any of my students got it right. So I was like, whoops, that's a wake-up call for me. I need to go ahead and change what I'm teaching and do better with the squeeze theorem. So, hence this lesson. I did mention that I'm like, oh no, none of my students got it right. Well, there are 24 short answer questions. So they missed one part of the 24 short answers. That really almost certainly affected none of their scores. So I didn't feel too bad. Again, it was just a wake-up call. We'll talk more about the scoring down the road too. But again, 1 or 2 multiple choice questions, 1 or 2 free response parts of those short answers, if they don't go well, it's not going to affect your overall score much, if at all. All right, so let's go ahead and look at the rest of these. Now, normally the squeeze theorem is presented in a manner that's a little more friendly to us because they're going to be multiple choice questions. The multiple choice part of the AP exam is not looked at in terms of work. You can show no work, lots of work, bad work. You don't have to worry about crossing out or erasing. I see a lot of my students do some work and they're like, oh, the limit as x approaches 1 of g of x. Then they're like, oh, no, wait, it's not g of x. It's not a limit. I'm really just finding like f of 7. Why would you erase? Erasing takes time. So if you really want, you can just cross something out and keep working on it, or you don't even have to cross it out. But again, nobody looks at the work for the multiple choice. All they do is they take your bubble sheet, they scan it, the end. There will be times, though, especially on your tests and your quizzes, that I will ask you and really demand of you that you need to show work like it was a free response question. And here, that is one of those cases. Please justify your answer using the same work as above. Right? Practice improves your performance. So there are 1, 2, 3, 4, 5 questions to go. You should strive to accomplish these without a calculator. And whenever you're done, or if you want to check one by one, you can unpause my video. We'll see how you did, and that should be it. Ready, set, go. Okay. Let g and h be functions defined by g of x, h of x. If f is a function that satisfies this, you'll notice that f is in the middle of these functions, right? What is the value of the following limit? Okay, well, we need to do something like such. I'm going to go ahead and find the limit of each one of the bordering functions, the squeezing functions, the bread of the sandwich for this sandwich theorem. And since we're talking about the limit as we approach 1, I'm going to find the limit as x approaches 1 of g of x first. Now, it is okay for you to just put this function in here, but I like to be pretty thorough here. So I'm going to say I'm going to find the limit of g of x, since it's stated here. And to do that, I'm going to find the limit as x approaches 1 of negative 2x squared plus 4x plus 1. And now I'm going to actually substitute in 1 for the x's. As soon as you substitute in 1, you're finding out what happens at the point. You're not actually finding the limit anymore. But we know for any sort of polynomials like these that the limit and what happens at the point are the same. So once I substitute in 1, you don't need the limit anymore. You can put it if it makes you happy, but it's pretty redundant. Okay? So once we're here, we end up with negative 2 plus 4 is positive 2 plus 1. I'm getting 3. Then I'm going to find the other one, the limit as x approaches 1 of h of x. It's my upper bound for my functions here, and that's going to be the limit as x approaches 1 of 1/2 x squared minus 3x plus 11 halves. So we end up with 1/2 by 1 squared minus 3 times 1 plus 11 halves. What does this give me? 1/2 times 1 is 1/2. 1/2 plus 11 halves is 12 halves, right? So we'll put that just as a little placeholder. So that took care of those guys. And then we have negative 3 times 1 is negative 3. Okay, so this becomes 6 minus 3, which is also 3. Well, that's cool. So I'm pretty convinced then that the limit as x approaches 1 of f of x is 3. So are we done? It seems like we have some work for the because, and we're actually not. Right? There's two things that need to happen in order to use the squeeze theorem, in order to conclude here. And we are using the squeeze theorem. Even if you're like, we didn't say squeeze theorem, the only way you actually know that is through two things. Not only do the limits have to be equal, but also this needs to be true, and you do need to restate that. So, and g of x is less than or equal to f of x, which is less than or equal to h of x. So this limit is true because of all this. Now, you could say, because of all this, the squeeze theorem says that this is true, but again, the squeeze theorem is going to be a little bit irrelevant here. So we end up with A. Or not irrelevant, but redundant, not needed. Okay, problem 2. Oh, this one looks pretty darn similar. Gives you a nice chance to do some trig functions, but we get the idea, right? So let's try it again. We're approaching -1 this time. Start with g of x. The limit as x approaches -1 of g of x will be the limit as x approaches -1 of sine of pi over 2 times x plus 2 plus 3. Notice this is just sine of all this and the plus 3's at the end with those parentheses, which will be sine of pi over 2. -1 plus 2 is +1. So this becomes sine of pi over 2. And sine of pi over 2, if I remember correctly, is 1. So 1 plus 3, I'm getting 4 here. Then we'll work with h of x. Same idea. Get that limit practice in. Anytime you have x in there and you're saying these are equal, you need that limit. And so this is -1/4 x cubed. It's 3/2 x squared minus 9/4 x plus 3. Okay, well, we have to substitute in -1, which could start to be interesting. -1 cubed is -1 again. -1 squared is 1, so that's just minus 3/2. -1 times -9/4 will be +9/4 plus 3. I'm going to need a little bit more room here, I think. So we're going to drop down. This becomes +1/4. Right? And then they're fourths, so let's go ahead. If I do +1/4, 9/4, that's 10/4. Kind of reduces. Sure, we can work with that. So, oh yeah, I could have just made this 10/4, and that comes from 1/4 and 9/4, right? It gets us 10/4. And 10/4 is eventually going to reduce, right? So 10/4, I'm going to cross this out and just quickly reduce it, divide by 2. That's 5/2. And the reason I didn't want to change this is because that's 3/2, right? Now we're looking pretty good. 5/2 minus 3/2 is 2/2, which is really just 1, and 1 plus 3 equals 4. All right, limit of the lower function, limit of the upper function, they're both 4. I'm pretty darn convinced then that the limit of the inner function is also 4, but we're not done. There's two things in order to conclude with this. This is my conclusion up here, right? Because this and g of x is less than or equal to f of x, which is less than or equal to h of x. So, squeeze theorem, there we go. Looks like 4. Okay. Here's 3. We have g of x, h of x. We're getting the idea now. I love this. We should be just fine. So here comes g of x. The limit as x approaches -1 again of g of x equals the limit as x approaches -1 of -x squared minus 2x plus 3. It's going to test you on your PEMDAS here, so I should probably write this out and make sure we don't get too confusing. -1 squared is +1, and then make it negative. So this whole thing is -1 here. This is +2, and then of course +3. 5 minus 1, I'm getting 4. And then we'll work the upper function. The limit as x approaches -1 of h of x equals the limit as x approaches -1 of this function. More fractions. Who decided on these problems? Spoilers. It was I. Sorry. 1/2 -1 squared plus -1 plus 13/2. Seen some halves. Let's combine those first. This is +1. This is +1/2. 1/2 plus 13/2 is 14/2. This becomes -1. 7 minus 1, I'm getting 6 here. Oh, let's see. The lower limit was 4. The upper limit was 6. So what do we conclude then? Well, because we know f of x is between g and h, can we say that f of x is 5? It seems to make sense, right? No, we can't do that, right? If you picture a graph, we're talking about what happens at -1 over here. Here is 4. Here is 6. What ends up happening is the red function is doing whatever we want. It's the lower function, right? But they said that the limit as we came over here was 4. I'll do closed circles to make it easy, okay? And then the purple function, which is the upper function, is doing whatever it wants, but we said at -1 the limit was 6. So I have two made-up functions here, and my g of x function, or f of x function, which I'll do in green here, doesn't have any restrictions except that it's in between red and purple. So what if it went through and kind of had this point up here and then went back down, and this point was actually at 5.9, right? This point can be anywhere in between those two. And so if the two limits are not equal, we cannot apply the squeeze theorem, and we say the limit cannot be determined, right? So this limit, as we approach -1 of g of x, is not equal to the limit as we approach -1 of h of x. Therefore, no squeeze theorem. Okay. Now, sometimes people have a habit of saying, oh, if you can't use the squeeze theorem, the limit doesn't exist. Well, that's not actually the case, right? That's not right. This limit could still certainly exist, right? It exists up here. It could be 5.9. We just can't determine it using the squeeze theorem. If a theorem doesn't have its criteria met, it does not automatically mean, oh, there's no answer here. It just means we might have to find a different way to find the answer. But since we're focusing on the squeeze theorem, for now, if we can't use the squeeze theorem, we just say we can't find the limit. Could still exist, just can't find it. All right, 2 to go. Let f, g, and h be these functions. All of the following inequalities are true from -1 to 1. Which of the inequalities can be used with the squeeze theorem to find the limit of the function as x approaches 0? Justify your answer. So it could be 1, could be 2, 1 and 3, or 2 and 3. I think we're going to have to work through and look at 1, 2, and 3 all together. So let's go ahead, and this is a multiple choice question I asked you to justify. We aren't going to have a ton of space here, but that's okay. I think we'll be all right. So let's go ahead and find all of the limits as we approach 0. And I'm just going to do kind of the work over here. The limit as x approaches 0 of 1/4, that's a constant, is just 1/4. Here, the limit as x approaches 0 of x squared plus 1/2, so we're taking the limit of the whole thing, substitute in 0 is 1/2. So for number 1, notice that the limit as x approaches 0 of 1/4 is not equal to the limit as x approaches 0 of x squared plus 1/2. Therefore, no squeeze. All right, so we know that 1 is out, which eliminates A and actually C as well. So let's go ahead and try option 2. Okay, option 2 I'll do in green. We need to find the limit as x approaches 0 of -x to the 4th, which is 0, right? And we also need to find the limit as x approaches 0 of x to the 4th, which is also 0. Well, that looks pretty good. I bet we could use the squeeze theorem to find the limit of the functions, right? And I'm just going to write it out properly. I'm going to say -x to the 4th is less than or equal to g of x, which is less than or equal to x to the 4th, and the limit as x approaches 0 of -x to the 4th equals the limit as x approaches 0 of x to the 4th. Therefore, the limit as x approaches 0 of g of x equals those two, and they both equaled 0. We should probably say this equals 0. We did that up above, but not a bad thing to write it back through. So 2 definitely works. So it could be B. Unfortunately, it could also be D. On the AP exam, there is always one right answer on the multiple choice. There is never a select all. It's 4 options, and you only pick one. It used to be 5 options. Now it's 4. All right, so let's do the last one, our tiebreaker down here. We need to find the limit as x approaches 0 of 1 over x squared, and the limit as x approaches 0 of negative 1 over x squared. Okay, now if you substitute in 0, you get a constant over 0. And the constant over 0, the safe way to say that is does not exist. Same thing over here. This one would be does not exist. Now you might look at this and say, ooh, there does not exist. Does that mean that they're equal? And the answer is not necessarily. Okay, the graph of 1 over x squared looks like this. It's not something you have to know, but that's okay. And so actually, this limit, if you wanted to be more accurate, would be positive infinity. And the graph of negative 1 over x squared, if you apply a negative, it's just going to flip it all downwards, is going to be negative infinity. So although they are both does not exist, the safe answer, the more accurate is infinity and negative infinity. However, our squeeze theorem actually has to equal L a value, and that has to be between negative infinity and infinity. So we cannot apply the squeeze theorem here. Our answer is going to be B, right? So nothing too bad. We got it. We got to discuss our does not exist case, okay? And we're going to move down to our last problem. Oh, I guess I should have mentioned this too. Ha, awkward. They defined f, g, and h. And they said where x doesn't equal 0. So what that really means is that when you substitute 0 in for each of these, you get a discontinuity. Now, I doubt any of us know what these graphs look like. I don't particularly off the top of my head, maybe 1 or 2 of them. But what that really tells us, though, is that there is no point at 0. Which is why we were trying to examine them and say, okay, we can't find the point at 0, but can we see what those functions are approaching? Okay, and so our answers here are that we could not see what this is approaching. By the way, this limit does exist at 0. I think this limit ends up being like 1/2 or something. This limit we know definitely exists at 0 because of this. But the reason I mentioned the first one is the squeeze theorem didn't work there. Right? The squeeze theorem was no good, so we couldn't actually say what it was. However, there is still a limit that exists. Okay, last problem. We have 3 more graphs. Again, you probably don't know what they look like, and that's okay. And we just have to do the same thing as before. Now, though, we're again looking as x approaches 0. We have slightly different functions. Okay, I bet you can go through and figure this one out no problem. I'll just do the basics of the work, though. As x approaches 0, 1/3, 1 minus x squared, 0, 1. This ends up becoming 1/3. Over here, this limit, just showing my correct notation of a constant, is certainly 1/2. They're not equal. We know that 1 is out. That one's out as well. Okay, if we look at 2, I think visually we can see on 2 as we approach 0. 0 is certainly the same, so 2 works. I like that one. And then we check 3. 3 is going to have the same issue, where if you substitute in 0, you get do not exists, and so 3 is out, and we just end up with B. Very, very similar to the one up above. All right, and that is really it for today. This is probably one of our shorter videos for the unit. Excellent. And that is about all. So we only have a couple lessons left. I think there are about 10 or so lessons in this unit. We just did day 8, so maybe 3 more lessons to get to 1.10. Thank you as always for tuning in. If I made any mistakes or you'd like me to address any further questions, leave them in the comments. And I'm excited to have you back next class for lesson 1.8.